Introduction to PyTorch. PyTorch is a popular Python library for deep learning. It is used to build and train neural networks. PyTorch is known for its flexibility and ease of use. You can use PyTorch for research, production, and prototyping. PyTorch has real-world uses in image recognition, natural language processing, and more. Running the cell now. We will install and import PyTorch and its related packages. On Windows, use pip to install. This line suppresses warnings so your output is clean. This line imports the system module, which is useful for system-specific tasks. This is a comment. To install PyTorch on Windows, you have to use pip in your terminal. This is a comment showing exactly what to type to install the packages. This line imports the main PyTorch package. This line imports Torch Vision, which helps with images. This line imports Torch Audio, which helps with audio. Running the cell now. This code sets up the PyTorch environment by importing the core libraries needed for deep learning, Torch, Torch Vision, and Torch Audio, without producing visible output. Notice that no output is expected here because the intent is to prepare your workspace for building and training neural networks, reflecting the initial setup step in a PyTorch lesson. Core PyTorch objects and concepts. PyTorch uses tensors, similar to arrays. Computations can run on the CPU or GPU. Neural networks in PyTorch use the NN module class. Autograd automatically computes gradients for training. Running the cell now. Let us create a basic tensor in PyTorch. Import the Torch library. This comment tells us we are making a simple tensor. This line creates a tensor with values 1, 2, 3, and 4. This prints the tensor to the screen. Running the cell now. This output shows a PyTorch tensor created from a simple Python list. Notice how the tensor's shape matches the input list length, confirming it's a one-dimensional array of 4 elements. This demonstrates the foundational concept that PyTorch's core data structure, a tensor, can be easily created and displayed, forming the basis for more complex computations on CPU or GPU. Now, let us look at a two-dimensional tensor. This comment reminds us that tensors can have more than one dimension. This line creates a two-dimensional tensor. This prints the two-dimensional tensor. This line prints the shape of the tensor. Running the cell now. This output shows a 2x2 tensor, highlighting that PyTorch tensors can be multi-dimensional arrays. Notice the shape attribute confirms the tensor's dimensions, which is crucial for ensuring tensors are compatible in computations and neural network layers. This reinforces the lesson's introduction to tensors as core data structures in PyTorch. PyTorch can use GPUs if they are available. Let us try moving a tensor to GPU. This comment explains that we will try to use the GPU. Check if your system has a GPU available for PyTorch. If you have a GPU, this moves the tensor to the GPU. Print a message if the tensor is now on the GPU. If you do not have a GPU, print a message saying you are using the CPU. Running the cell now. This output indicates the device where the tensor will be processed, confirming the code's intent to leverage GPU acceleration if available. Here, since no GPU was detected, the tensor remains on the CPU, which is typical when working on machines without CUDA support. This decision impacts the speed of subsequent computations and highlights PyTorch's flexibility in handling different hardware seamlessly. Beginner PyTorch examples. Create tensors from lists and Numpy arrays. Do simple math using tensors. Convert tensors to Numpy and back. Running the cell now. Let us create a tensor from a Numpy array. Import Numpy, which is used for arrays. This comment explains we are making a Numpy array. Create a Numpy array with values 5, 6, 7. Turn the Numpy array into a PyTorch tensor. Print the tensor. Running the cell now. Here, the code creates a Numpy array and converts it into a PyTorch tensor, preserving the original data and shape. Notice that the tensor output exactly matches the Numpy array values, demonstrating how tensors can be easily created from existing Numpy data. This is key for beginners to understand how to switch seamlessly between Numpy arrays and PyTorch tensors for efficient computations. You can add tensors just like numbers. This is a comment saying we will add 2 tensors. Make a tensor with values 1, 2, 3. Make another tensor with values 4, 5, 6. Add the 2 tensors together. Print the result. Running the cell now. This output shows the element-wise addition of 2 tensors, producing a new tensor with values 5, 7, 9. Notice how each element in tensor A is added to the corresponding element in tensor B, demonstrating simple math operations with PyTorch tensors. This reinforces the lesson's focus on creating tensors and performing basic arithmetic on them. You can also turn a PyTorch tensor back into a Numpy array. This comment explains we are converting the tensor back. Convert tensor C to a Numpy array. Print the Numpy array. Running the cell now. Here, we see the output, 579, which is a Numpy array converted from the PyTorch tensor C. This demonstrates how tensors created and manipulated in PyTorch can be seamlessly converted back to Numpy arrays, allowing you to interoperate between PyTorch and Numpy for flexible data processing. Intermediate PyTorch examples. Create random tensors. Use Autograd to calculate gradients. Use basic neural network layers. Running the cell now. This makes a tensor filled with random values. This comment explains we create a random tensor. Make a 2 by 3 tensor of random numbers from a normal distribution. Print it. Running the cell now. Here, we create a random tensor with shape 2, 3, which means it has 2 rows and 3 columns, reflecting a small batch of data or features. Notice the values are drawn from a normal distribution, including both positive and negative numbers. This step is key for initializing inputs or parameters before building more complex neural network operations. Let us use Autograd to find gradients. This comment tells us we will use Autograd. Create a tensor with required gradient tracking. Calculate y as a function of x. Sum the elements to get a single value. Call backward to compute gradients. Print the gradient for x. Running the cell now. This output shows the gradients of the function \y is equal to x squared plus 2x plus 1 / with respect to each element in tensor \x \. Notice how x.grad holds the derivatives \6, 8. \, which are calculated as \2 * 2 plus 2 equals 6 \, and \2 * 3 plus 2 equals 8 \, matching the manual gradient of the quadratic expression. This demonstrates Autograd's power to automatically compute gradients, essential for training neural networks. Let us build a simple linear, fully connected layer. Import NN, which has neural network tools. This comment says we will make a linear layer. Make a linear layer that maps for inputs to 2 outputs. Create a random input tensor with 1 row and 4 columns. Pass the input tensor through the linear layer. Print the output. Running the cell now. Here, the output tensor shows the result of passing a random for-element input through a linear layer, transforming it into a 2-element output. Notice the shape 1, 2, reflecting one sample with 2 features, and the presence of grad_fn indicating the output is ready for gradient computation. This connects to the lesson by illustrating how basic neural network layers process data and maintain differentiability for Autograd. Advanced PyTorch examples. Use the Dataset and DataLoader for batching data. Build and train a custom neural network. Running the cell now. Here is an example of how to create and use a custom dataset with PyTorch. Import Dataset and DataLoader for handling data. This comment explains we will define a simple custom dataset. Define a new dataset class named MyDataset that inherits from dataset. Initialize with a tensor of numbers 0 to 9. This stores the data as a tensor. This returns the length of the dataset. This returns one data item given its index. Create an instance of MyDataset. Create a DataLoader that makes batches of size 3. Loop over the batches and print each batch. Running the cell now. This output shows how the DataLoader splits the dataset into batches of size 3, yielding tensors of sequential elements from the original data. Notice that the final batch contains only one element, demonstrating how PyTorch handles any leftover data when the dataset size isn't a multiple of the batch size. This batching process is essential for efficient model training in our custom neural network. Now, let us build a small neural network class in PyTorch. Import functional tools from NN for activation functions. This comment signals that we will build a custom network. Define a new network class, net, based on NN module. Initialize the network. Call the init of the parent class. Add the first linear layer, 4 to 3. Add the second linear layer, 3 to 1. Define the forward pass, how data moves through the net. Pass through the first layer and apply ReLU activation. Pass through the second layer. Return the result. Create an instance of the model. Make a sample input tensor with shape 2, 4. Run the model on the input. Print the output. Running the cell now. This output shows the raw predictions of the custom neural network for a batch of 2 samples, each with 4 input features. Notice the output shape 2, 1 matches the batch size and single output unit, confirming the model processes inputs in batches as intended. This demonstrates how the network transforms input data through layers to produce continuous valued predictions, key for training in PyTorch. Error handling and debugging. PyTorch will show errors if tensor sizes do not match. Use print to check intermediate values. Use try except to catch errors. Running the cell now. Let us see what happens if you try to add tensors with different shapes. This comment explains we are showing a common error. Create a 2 by 3 random tensor. Create a 4 by 3 random tensor. Try to add the tensors. This line would add the tensors. Catch the error if shapes do not match. Print the error message. Running the cell now. This output shows a size mismatch error when trying to add tensors of shape 2, 3, and 4, 3. Notice how PyTorch clearly indicates which dimension sizes conflict, helping you quickly identify the problem. This reinforces the lesson's point. Using try except and print statements aids in debugging tensor shape issues before they cause program crashes. You can use print statements to debug inside your own network class. This comment reminds us to print for debugging. Define a debug network. Start the initialization. Call the parent class constructor. Add a linear layer mapping 2 to 2. Define how forward pass works. Print the input to the network. Pass input through the linear layer. Print the output values. Return the output. Create the debug network. Make a random input tensor. Run the debug network. The prints help you see what happens. Running the cell now. This output shows the shapes and values of the input tensor and the resulting output tensor from the linear layer. Notably, both have a shape of 1, 2, confirming the sizes match as expected. Printing these intermediate values helps verify data flow and catch shape mismatches during forward passes, which is crucial for effective debugging in PyTorch. Best practices in PyTorch. Always check tensor shapes as you code. Put your model in eval mode when evaluating. Use with torch.no_grad to save memory when not training. Save and load model weights using torch.save and torch.load. Running the cell now. Let us see best practice, use eval and no_grad for evaluation. This comment says to set the model for evaluation. Set the model to evaluation mode. Do all lines inside with no gradient tracking. Create a random input tensor. Apply the model without computing gradients. Print the output. Running the cell now. Here, the output tensor has shape 2, 1, matching the batch size of 2 inputs and a single output per input, confirming the model's expected behavior in eval mode. Using model.eval ensures dropout and batch norm layers behave consistently, and torch.no_grad saves memory by disabling gradient tracking during evaluation. This demonstrates the best practice of verifying output shapes and modes while evaluating your model. You can save and later reload the weights of your model. This comment tells us we will save and load the model weights. Save the learned weights to a file. Create a fresh model instance. Load the saved weights from the file. Put the new model in evaluation mode. Print a message that the model is ready. Running the cell now. This output confirms that the model weights were successfully saved and loaded into a new instance, which is now set to evaluation mode for inference. It highlights the best practice of separating model definition from its learned parameters and ensuring the model is in eval mode before making predictions. This step is crucial for consistent and efficient evaluation without tracking gradients. PyTorch mini project, linear regression. We will fit a line to simple data using PyTorch. This is similar to y equals mx plus b. We will create fake data, make a model, train it, and see the result. Running the cell now. Let us start by making some fake, synthetic, data for linear regression. This comment says we will make data. X is a column vector from 0 to 1, 10 points. Y is 2 times x plus 1, with a bit of random noise added. Print the x values without the extra dimension. Print the y values the same way. Running the cell now. Here, we created 10 evenly spaced data points for x between 0 and 1, and generated corresponding y values roughly following the linear equation y equals 2x plus 1, with some noise added. Notice how y trends upward as x increases, which reflects the positive slope we expect to learn during training. This output confirms our synthetic dataset is ready for fitting a linear regression model. Now we will define and train a simple linear regression model. This comment explains we will make a linear regression model. Create a linear layer with one input and one output. Make an optimizer using stochastic gradient descent. Define our loss as mean squared error. Train the model for 100 steps. Compute the model prediction for all x. Calculate the loss by comparing predictions to targets. Zero the gradients before the backward pass. Compute gradients with backward. Take an optimizer step to update weights. Every 20 steps, print out the current loss. Print the learn parameters after training. Running the cell now. This output shows the training loss steadily decreasing over 100 steps, confirming that our linear regression model is learning to fit the data more accurately. The final train parameters approximate the slope, (2.09), and intercept, (1.0), matching the expected form y equals mx plus b, which demonstrates successful model convergence. This aligns with our lesson goal of fitting a simple line to fake data using PyTorch. Let us make a prediction using our trained model. This comment says we will test the model. Make a test input with value 0.5. Turn off gradients while testing, saves memory. Get the prediction for the test input. Print the predicted value. Running the cell now. The output shows the predicted y value for the input x equals 0.5 using our trained linear regression model. This value, approximately 2.04, demonstrates how the model applies the learned line equation y equals mx plus b to make predictions on new data points. It confirms that our model is ready to generalize beyond the training samples. Thanks for learning PyTorch. Please subscribe if you find this helpful. Watch our other Python tutorials on the channel. Running the cell now.